Welcome back to our discussion of the second half of Chapter 10, Solubility, Product, Equilibrium. We are trying to quantify the effects of adding a common ion to a particular reaction. We chose last time as our reaction lead to iodide, mostly insoluble salt. Add some of it to water, it would definitely look like nothing is happening. But a little bit of the lead and iodide does ionize, does dissolve in the process, and it sets up that equilibrium. With this KSP value, which we get from the textbook or some other chart of KSP values, we did all of this, a Rice table, calculated KSP, did a little bit of, there's a cube root in there, no big deal, your calculator handles that, you don't have to handle that. Okay, so we do all that work, and we found that the concentration of lead before I add a common ion is at 0.0013 molarity. So I could throw in as much lead to iodide as I want, and about the only amount that will dissolve is 0.0013 moles per liter. So very, 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 very small amount of it will actually dissolve. But what we want to investigate is what happens when I add a common ion, when I add some sodium iodide. Now you need to recognize a common ion. That's how you recognize it. You see the same ion there. Now I could have added something that added lead, and that would still be a common ion. In this particular case, I'm adding iodine. It just happens to be the situation. Okay, so let's look at what changes this makes to our calculations, and then we'll be able to compare the concentration of lead with the common ion compared to the concentration of lead without. We would expect already that the concentration of lead to decrease with the common ion because we expect that equilibrium to shift back to the left and use up some lead ion to make more lead solid. But let's find out. So I have my reaction. PbI2 is going to make Pb2 plus and 2y minus. And initially, okay, it really doesn't matter how much initially I have of that. We discussed that last time. Go back and review that video if you need to again. Initially I had 0 lead, but check this out. 0.20 molarity of sodium iodide will one-way arrow into sodium ion and iodide ion. It's a go-to-completion reaction. It is very soluble. And with that small amount in there, we can virtually guarantee all of it's going to ionize. That's a very good assumption. So with the ratio of 1 to 1 to 1, 0.02 molarity sodium iodide becomes 0.20 molarity iodide ion. So now I'm actually starting with some iodide ion. Okay, so now for the change. I'm going to make some lead. I'm going to make 2 times that amount of iodide. So at equilibrium, I have X for lead, and I have 0.20 molarity plus 2X for the iodide ion. Let's write our KSP, get a point for writing your formula, concentration of lead to iodide. Times the concentration of, wow, we don't want the 2 there, iodide ion squared because it needs to go there. There was 1 lead, but there was 2. The coefficient of 2 becomes our exponent. Okay, so point for that. Now, KSP stays the same, 9.8 times 10 to the minus 9. Lead is still X, but check it out. Check out what iodide is now. Iodide is 0.20 molarity plus 2X. And then that is squared. So to solve this, I'm going to have to FOIL and distribute that 2 to, square this, square that, inside terms, outside terms. Lots of fun there. Then I actually work another X through all that. So I'm going to end up with an X to the 3rd in there. So this is going to get complex super fast. We would need something even more than the quadratic equation to solve it. Let's not go there. Remember what we did back in general equilibrium that allowed us to make the algebra easier? My claim is very little lead in the first place is ever going to ionize, which should mean very little iodide in the first place would ever ionize. Meaning this little bit here added to that is still going to approximately be 0.2 molarity. Okay, so this is where I would assume, because K is very small. Make a statement somewhere. And yes, let's jump 2 screens ahead. There we go. Assume because K is very small that 0.20 molarity plus 2x is approximately 0.2 molarity. So now I get that. Oh, doesn't that look a lot better all of a sudden? I don't even have an x now in that term. Check that out. I have 9.8 times 10 to the minus 9 equals 0.2 squared, so 0.04 times x. So now we're going to solve for x. Okay. So yay, calculator time, because we always have so much fun with calculator time, right? So a reminder, you're going to square 0.2, and then you're going to divide the 9.8 times 10 to the minus 9 by that square of 0.2, which is 0.4. And if your calculator has a squared button, you don't even have to bother doing that ahead of time. Okay, that's between you and the calculator. Learn how to use your calculator well. All right, so x is 2.5 times 10 to the negative 7 molarity, because what does x stand for? Well, x up here stood for the concentration of lead. So that is the new concentration of lead 2 ion. Okay. Now, real fast, was I correct in my assumption? Well, yeah, that goes to the 10th place, and this goes to like the 10 millionths place. So that little bit of plus 2x is going to make zero difference by the time we round to our appropriate significant digits on this. So yes, my assumption was most definitely correct, and it is more than likely going to be correct for all of KSP, because by definition we're looking at things that are very, 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 very tiny amounts of solubility. So we're looking at very low numbers for K. So do expect to make the assumption. It even works out in this case to simplify the math. Be sure you make a statement when you do that. Now, we really have not answered the question. My new amount is 2.5 times 10 to the negative 7 molarity. Or in other words, 0.123452625 molarity. Okay, now let's go back a slide and compare. Here is my new molarity. Here is my old molarity, 0.0013. So without the common ion, 0.0013, notice that's only 2 zeros, dissolved. And with the common ion, I had now 6 zeros in there. So does adding a common ion make an effect in the solubility? Most definitely. And you can predict that with Le Chatelier's principle. If I'm adding a product, iodide ion, it should shift the equilibrium to the left. That leftward reaction will speed up for a while to get back to equilibrium. And when it gets back to equilibrium, this will be the concentration, my new concentration of lead. And I'll have roughly approximately that much iodide ion at that new equilibrium. All right. So that is a numerical demonstration of the common ion effect. It is a not unusual thing to happen when they're talking about solubility product on the test. They more than likely would ask a common ion question. So let me say this again. What effect does adding the common ion have? You should be able to explain it with Le Chatelier's, but you should also be able to point out numerically what effect it has. By adding a common ion, this section here, check it out, that changed our initial amount. So it's going to numerically change our Rice table, and that should numerically change our KSP calculations, which should numerically change your concentrations. And again, I could have just as easily added in lead ions and searched for iodide ions and still had a common ion effect. So don't get used to it being always the negative ion. It could be either. All right. So KSP will not only tell us how much of an insoluble salt would dissolve and ionize, but it can also tell us how much of an ion would be needed to get a precipitate. We could even do this to selectively precipitate out one ion from a mixture in isolation from all the others. So we call that selective precipitation. So say I have a mixture of mercury, silver, and copper. Why not? Okay? They're all dissolved because I use like mercury nitrate and silver nitrate and copper nitrate. They're all dissolved to a very, 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 very small amount because they won't dissolve much even as a nitrate. Okay, but very, very small amounts dissolved in a test tube I have. But I want them separated. Well, if I could find a way to get, say, this is hypothetical, just get the copper to precipitate into a solid only, leaving these in the solution, then I could filter out the copper and I'd have the copper. And then in my solution would still be these two. And then I would do something else to maybe filter out the silver. And then I would have the copper in one filter paper. I'd have the silver all in another filter paper. And I would have the mercury still in the solution. And then if I needed it as a solid, I could add something in to make it a solid and filter it out too. So selective precipitation uses the common ion effect. It's a way to add a common ion until these start precipitating out, typically one at a time. So we should be able to calculate how that's going to work. But that is a calculation that does start getting involved. So we'll pick up there for next time. I want you to practice the basic common ion effect with, what effect does having one common ion effect to the solubility. So good luck.